So, how do we really reduce the complexity of that? So, we need to start from the training samples, right. So, this is the source preparation that I had shown earlier. If you look at this, there are many bigrams that are repeating. Okay. Let me show some examples. See, for example, the words like of the or the pairs of happy returns the do not give much information about the words happy and return, correct. The context is not good enough in the bigram model. So, in the same fashion, if you expand it to trigram, there could be some combination where the context word will not give you any meaning to the target word that you are looking at, or the target word will not give you any meaning to the context that you are looking at. Some words we can remove at random. Similarly, some pairs reappear with the order of the words switched. Okay. So, you will find some of the words here as well. For example, say here, right, the words are switched. So, we can actually reduce this, instead of keeping those two as the training sample, we can reduce it to 1. So, in this fashion, if you find these kinds of duplicates, even the words are switched within the bigram or trigram or 5gram that you are looking at for your context, you can remove them. And then certain words like the combinations like of the do not really give any meaning to the processing. So, same word, same here. Okay. So, in the model, this is just a simple example. We do not normally use bigram for doing the training. We normally go with at least 5 words window, correct. So, this is called subsampling. So, when you remove these words from the samples, you get a smaller subset, and then you use that smaller subset to train the network. So, because of the size that increases along with the number of vocabulary you have, right. So, we have to somehow reduce the training sample. So, this is one way to reduce the training sample. We can also remove certain words from the vocabulary based on the frequency. Suppose if some words appear only once in the entire corpus, that is not going to give us any context, correct. So, we can probably remove that word from there. Okay. Again, some, as I mentioned earlier, some of the words that appear as context words could be discarded if they do not give any contextual information to the central word that we are talking about. Okay. So, now what I have in this slide is a real example that used in a C program. This is actually a C program written by Google to really demonstrate their word to vec model. This is implemented using skipgram. Okay. So, here they have used some subsampling mechanism to remove the infrequently occurring words. Okay. So, if you really understand C, I would like you to go through this and then see how really they are utilizing the mechanism to really reduce the number of samples for the training. Okay. All right. So, there is another mechanism by which you want to minimize the computation, right. So, that is called negative sampling. I keep repeating this several times. The computations of this model is very huge when the vocabulary size is very large. Okay. So, each and every weight updation costs money. Okay. So, we need to be able to reduce the number of operations in the entire a back propagation model. So those are the ideas which we are now using to reduce the number of computation. This is one, subsampling is one. The second one is negative sampling. So why should I update all my weights every time when that don't really make any impact in the learning? Okay. So which are those weights that I should not really bother about? Okay. So when you look at that, right, the learning that happens only for the context words and the input word, correct. The rest of the words, there are some errors that happen and they really don't impact on the training when we train the set of context words and the target words, or when you use the in the skipgram model, when you use the input word and try to predict the context word. Rest of the words don't really contribute anything to this. So can we really curtail the updation of the weights by only choosing certain number of weights to be updated and so on? So that's where negative sampling comes into play. So in this case, for every training cycle of input, we update every weight, right? That's what we have been doing. And then softmax function computes the sum of the output neuron values. So it's again a huge computation for us, right? And then the cost of updating all the weights in the fully connected network is very high. So is it possible to change only a smaller percentage of weights? Okay, so that's where negative sampling come into play, and then let's see how this is done. So how do we really solve the problem that we have mentioned earlier, right? So now select only a small number of negative words. I'll talk about what that negative words. Okay, while updating the weight, these samples output 0, while the positive samples will retain the value. For example, if we have about 5 values that we want to retain, we call them as positive samples, and then we select 5 more values, okay, and then make them as 0, because we want them to be 0. Number of operations that you are going to be performing is going to be only on these positive values and the negative samples, right. So when you do that, we reduce drastically the computation. Instead of computing every weight in the embedding as well as the context matrix, we are going to be only changing certain number of weights. Okay. And this is what is given here. While updating the weight, these samples output 0, while the positive samples will retain the values. During the back propagation, the weights related to the negative and positive words are changed, and the rest will remain untouched for the current updates. We do not touch any of the other weights, we only change these 5 or 10 weights that we have chosen. So this drastically reduces our computation, isn't it? Instead of updating, for example, if you look at 1 million vocabulary by 300 hidden values, we have about 300 million weights to be updated every time, correct. That is for embedding weights as well as for context weights, leave alone your softmax computation and so on. So this we have reduced drastically by only choosing certain number of negative words. So these negative words are nothing but words in the vocabulary itself, but these words do not really contribute anything to the context word. They are not one of those context words. They are chosen through some mechanism, and they are taken, and those weights are updated. Okay. There are several mechanisms that are available, and this is one mechanism. So we want to be able to pick up only those most frequently appearing words as one of those negative samples. Okay. This I am sure you would know is the probability of a given word in the corpus, right. So, we are applying some mechanism which really boosts the probability of less frequent words and then reduces the probability of highly appearing words in the corpus. Okay. And then there is another mechanism. What you do is once you compute the probability and then find out how many times a particular word appears in the entire vocabulary. So, you have the frequency table as well. Using that frequency table, you can find out how many times you want to repeat certain words in a table. For example, you create a unigram table of size of the vocabulary and then pick up the most frequently appearing word and then copy them in the unigram table several times, okay, according to the frequency of the words, and then use this formula to pick a word or the number of words which you want to use as the negative sample. Okay. Okay. So, you got it. So, this is how we use find the negative sample and then use it in our computation of updating weights. So, as I mentioned earlier, the number of weights are phenomenal, right, for the computations. We want to be able to reduce that. For example, the word to weight given by Google uses 1 billion words and it contains about 30,000 to 40,000 words as vocabulary. And to train the network to generate the word vector, it takes about 40 minutes or 1 hour depending on your computer power.